Thank you very much. Thanks for coming, and thanks to the organizers for having me here. So I'm going to start off, with some challenges, and of course the reason we're all sitting in this room is AI, right? And AI is being used in a number of applications that we didn't foresee, say, 10 years ago. This is the Cambridge robot that's trying to act as a surgeon, surveillance, of course, in law, as well as financial trading. And I think, one of the concerns, or one of the reasons AI is sort of becoming such a hot topic in the news is that there are tons of concerns that come with AI. The first being they're sort of near impossible to verify, right? Depends on what you mean, of course. AI is a broad field. Everybody can hear me at the back? Yeah, okay, good. It's a broad field, of course, with many different techniques. But in general, what we see is that the way AI systems are built, it's a series of components that all come together. So it's quite hard to understand what exactly, happens, through this pipeline. And if you think about using machine learning, which is a branch of AI where you're specifically trying to learn from data, decisions taken are based on a lot of data points and in a very complex feature space. So by feature space, what happens is that they take these data points, they try to extract salient features from these data points and try to construct some kind of learning algorithm from these features. And these features, of course, for a person who's an expert in the domain, it might make a lot of sense, but all put together, it's quite hard to understand what's really going on. And as I mentioned, AI techniques are part of this complex data processing loop, right? There's data cleaning, and a fragment of this data goes to a machine learning system, and maybe some other kind of decision maker is taking, building something on top of these, and finally you get an output, or saying something like this person should be given a credit card or shouldn't. So it's quite hard to really understand what's going on, and it all boils down to the fundamental question: how can we trust the system? I think this actually presents quite some opportunities for us interested in applying AI. One of the, and I'm going to try to sort of emphasize 4 key points, I think, which are specifically opportunities that, that appeal to me, and I'm sure there are many others. The first thing is, I want to think about how you can make it easier for the systems to essentially incorporate human knowledge, right? This could be intuition, and as I said, in systems that you see today, this intuition is, deep in the whole decision framework, and what I want to do is make it a little easier to specify these decisions. One of the obvious, interesting things is, you have these complex systems. Can you enable interpretability in these systems? Can you make these decisions explainable? Can you ask for a reason for a certain decision being taken? And one of the other key points I want to focus on is this idea of data science democratization, right? So the idea is that, if you want to be using AI, you don't have to be necessarily a PhD, to apply these systems. It should be easier to actually understand and use these systems. So I'm going to aim for unsupervised methods, okay? So basically, these are systems which should be, in principle, plug and play. You put in the data and some magic happens, and you get a system out of it. Sort of the final point I want to touch on, which is, of course, to me, one of the more interesting intersections between AI and ethics, and many other philosophical point of view, is can you get machines to actually think about the implications of their decisions? Okay, so I'm going to focus on that point towards the very end, and the rest of the points are sort of going to be somehow orthogonally developed. So in sort of correspondence to the points that I sort of brought up in the previous slide, I'm going to try and talk about 4 different ideas, okay? All have somehow the same principles, but nonetheless, the development came about from different areas of research. One of the first ideas I'm going to talk about is this idea of a probabilistic program. The key motivation for this, this kind of programming paradigm is if you can make machine learning more modular and compositional. What does it mean? If you have 2 different machine learning components, can you bring them together in a very systematic fashion? Right, so that's probabilistic programming for you. The second part, if you, in the previous, I talked about interpretability, and these probabilistic programs turn out to be very interpretable. So the natural question is, can you actually learn these programs from data, as opposed to some expert specifying these programs? And the third point I'm going to talk about is, what if this program that you end up learning is too complex, too hard to understand, and can we shift our focus from focusing on looking at this kind of system that you learn to just to the query, the kinds of queries you can ask the system. And my fourth point is going to be, the fourth technique I'm going to sort of think about is responsible decision making. And to put all of this research in sort of a broader context, what I'm really trying to do is trying to look at the way you can combine machine learning with an area of research that's been very dominant in computer science from the 80s, which is symbolic systems. And symbolic systems is what you call as a model-based system. So essentially the idea is that you have some kind of partial or complete understanding of the domain. And what I'm trying to understand here is, can this kind of paradigm, influence and empower what's happening in machine learning? So that's the the context here. Let me take a few minutes to put this kind of research in a broader context. I don't know if many of you have been following in the news, but explainability is all the rave these days. And in fact, there's this kind of impressionistic understanding of different machine learning models and how they align themselves on this kind of explainability graph, right? So essentially, if you look at on the very top end, you've of course heard of deep learning, and deep learning has very high predictive accuracy, but of course they're not very understandable. Somewhere in between are classical machine learning methods, which you might have come across in universities, like graphical models and so on. And they're of course a little more interpretable, but they have less predictive accuracy. And then you have on the very far end where you have things like decision trees, which have this sort of disadvantage that they try to overfit your data. In terms of generalization, they're not very good, but of course they're very understandable, right? So I'm not going to really try and spread out this landscape for you beyond this slide. I'm just trying to give you a picture that there are many different approaches, and what's also become clear is that there is no single idea of explainable, right? So, people have a lot of disagreements. Some people think that explainability should really be about visualization. Some people think that explainability should be about reconciling the machine learning system with the kind of intuitions you have, about yourself. So trying to do what is called as model reconciliation. So I'm not going to talk about this landscape, just to sort of, give you a pointer that there is, an entire area of research really trying to understand what all of this means. And again, as a second aside, responsible AI is a big theme now, and are mainly driven by self-driving cars, or at least the idea that there might be self-driving cars in the future. And again, there are a whole bunch of topics here. One of the key topics is the idea of value alignment, and the idea says that how do you get the machine to actually understand your objectives? Right, and if you remember things like Asimov's laws, basically the idea is how do you get the system to, treat all humans in a reasonable manner, not cause harm and those kinds of issues. So there's a notion of value alignment. There's the issue of fairness. So, if you're trying to make a decision system that's predicated on somebody's profile, like, in a job application, you don't want this prediction to be based on gender, ethnicity, so on and so forth. And so the fairness topic really tries to bring to forefront what exactly does it mean to protect these sensitive attributes when you actually make the decision. And there's, of course, an area of research that's right up and coming now. How do you ultimately make AI beneficial for humanity, right? So at least the last bullet point really touches on, how philosophy is really trying to shape the goals of how AI research would go. And I don't want to belabor too much on any of these points. Again, just giving you a kind of pointer that there's a very broad area of research happening right now. And for both of these, both explainability and responsibility, I'm going to focus on a fairly narrow set of contributions that we've been trying to do, trying to address some of the technical issues that come up in this landscape. I want to set the stage, and in fact, we only have one actor here, and the actor is generative models. Just a show of hands, how many of you have an understanding of probability theory? okay, it's a fair number, you know, nothing's going to come up. I'm just trying to, you know, just trying to give you a perspective of where this is all going. And really, the kind of thing we're trying to do here is what is called as a generative model. And what generative model tries to do is it tries to give you a mathematical, you know, structure that can basically simulate your data. Can, you know, for instance, you know, one classical example is, you know, I'm looking at I'm a university, you know, administrator. I'm trying to understand, okay, if I look at all the, you know, if I look at all the graduations that happened before the year 2000, right? What is the probability that the pass, you know, the average mark, the pass record of students is greater than 50%, right? So, so what's really happening here is that I'm providing some observation. So this is called as conditioning, and I'm trying to extract the probability from it. And the whole point is that you're trying to do some kind of classification or labeling, right? You're trying to understand if these sort of features are triggered, what can I expect about the output, right? So imagine you're trying to, for instance, understand wines, and you try to say if the acidity is, you know, greater than 7 and it's coming from San Francisco, what is the probability that this wine is decent, right? So things like that. You know, the way people think about, you know, generative models is typically in terms of graphical models. Again, this won't come up in the rest of the talk. I'm just sort of giving you an idea of the kind of theory behind all of this. There is actually a more interesting development that's happening more recently where we move beyond simply looking at conditioning and we look at what is called as intervention. And this is what is referred as causality. And what happens in intervention is that you force some condition to become true, okay? So for instance, you're trying to understand, suppose I lower the entry requirements for students to my university. What will then happen to the probability of pass, right? So the difference between the two is in the first case, you're simply looking at a space of possible events, and you're saying, okay, I'm going to look at all my records that I have for the year, you know, before 2000. I'm going to see what kind of, you know, behavior do I see. And in the second case, you're manipulating, you're influencing and changing some variable, and then you're trying to see what kind of model comes out of it, right? And the most important reason, most important distinction with the second guy is that you may not have any kind of historical data to support this argument, right? Because you may not have actually ever tried to lower the, you know, the entry requirements of a university. So how are you going to come up with this kind of prediction, right? So just these 2 points. The causality aspect is only going to come up in the very last part of this talk, so just to give you an idea. All right, so the first thing I mentioned was probabilistic programming, and what exactly are these things? You know, at the very high level, these are basically languages to model probability distributions. Okay, so and the inspiration or, you know, the motivation for probabilistic programming is that they want to make machine learning more compositional and descriptive. So you're able to look at the program and sort of understand what's going on. If you know, in a very simple way to think about it is, you know, if you think about a programming language like Python, right? Typically, what you do is you have variables that you set to 3 or 4, you know, integers and so on and so forth. And the key distinction in these languages is that these things are not set to values, but they are random variables, okay? So I'll give you an example in the following slides, and there are many languages, and they can be used for modeling hidden Markov models in naive Bayes and so on. So here's a very simple example, okay? So think about this case that I'm trying to capture, again, a generative model of market fluctuations, okay? There is this variable which essentially tells me the chance of a foreign investment in my country, okay? So I don't have it's not deterministic, okay? So it could change year after year. So it's a stochastic variable, right? So based on whether there is actually investment, I get 2 different kinds of models, right? So this is what would be a mixture distribution. So basically what you do is that, for instance, so I'm going to say the chance of a foreign investment is really the toss of a coin, a biased coin. So they're not 50-50, but, you know, there's a 70% chance of investment coming in. I have these 2 models for my market fluctuations. so don't worry about the actual variables here, but I'm just trying to give you an idea, right? So you have A, which has which is again a fair coin toss, or you have B, which is a very unfair coin toss with a 1/4 chance of actually getting a heads and 3/4 of getting a tails, right? So what really happens is that you have this new variable called mix, which is capturing this mixture, right? And now you can take a step back from this model and you can say, okay, regardless of whether there's going to be investment or not, what is the probability that I'm going to get good returns, for instance, right? So you're going to define your queries completely on this new variable mix. Does that sort of make sense? More or less? So here's another example. I'm trying to capture the influence of a disease, okay? So I'm looking at people, and there's a 0.1 chance, there's a 10% chance that any person in this room could potentially get an infection, okay? And then I want to capture this model that if Y is infected and X gets in contact with Y, X is also going to get infected, right? So think of something like a common cold, right? And then, using just these two lines, I want to look at the spread of infection, right? I want to predict some things about infection, right? So that's the idea here. And as you can see, it's a fairly complex model, but what really happens in the program is just like 2 or 3 lines. I mean, this is not always the case. You do have programs with 100 lines, but the general feeling is that if in a classical programming language, it takes X number of lines, then it's substantially reduced when you have a probabilistic program. To give you a more complex application, which we looked at recently, so there's been a lot of focus, just to see how I'm doing on time. Okay, I should speed up a bit. There's been a lot of focus recently about trying to model questions from GRE and SAT, and the idea is that if you want to automate grading and help people, help students do much better on tests, some of these things should be automated so they can take tests quickly and repeatedly. And one of the things we observed is that some of these problems seem to have a very nice structure, right? So this is an example you might have seen in high school. Mike has a bag of marbles with 4 white, 8 blue, and 6 red marbles. He pulls a marble out of this bag and it's red. And what's probably the second marble he pulls out is white. So don't worry, I'm not going to ask you to calculate this. It's going to take me a while too. But the key idea is that the question actually breaks down into this nice syntactical form, which can then be written as a probabilistic program and you solve it. And of course now, if you think about this being as a part of an automated test, right, and the student answers, gives you some number and it says this answer is incorrect, it can actually trace and tell you what really went wrong. And why the calculation that the value that he gave was incorrect, right? So it takes a step towards explainability. What I am going to skip over these 3 slides, but what I wanted to actually capture here is the idea that you can deal with things that you don't know about. Okay, so maybe actually it makes sense to just talk about the very first slide. This is an example where I'm picking a block of wood. Okay, and I don't know what color it's going to be. Okay, so the question is, how would you actually capture this kind of setting in a program? And the way it would be captured is this. So if I pick something and it happens to be a piece of wood, right, and the color is going to come from a uniform distribution on, say, black or brown, right? So essentially, you don't have to know exactly all the objects in your domain. You can allow for a fair number of stochasticity when you model these problems. To really put this application in perspective, here's an example which is very commonsensical to our way of viewing things, and I'm just going to read out what it says. So let's look at the bottom line first. It's supposed to be read right to left. Okay, so what it says is that if A is inside C, right, and C is inside B, then A is inside B, which makes sense, right? So you're just talking about the transitivity of boxes. And the bigger thing on top, what it says is that if I put an object on top of another object, and the second object happens to be hollow, it's just going to fall through, right? Which makes a lot of sense. You agree? Yeah. And so this was how we tried to sort of, you've all heard of object tracking, which is being used in a number of applications from your cameras, to surveillance and so on. And what we were trying to do is, so you can see that the smaller box is placed in the bigger box, and of course it falls through. And at that point, right, as far as the vision system is concerned, it's just seeing one object. But because we have this program, it actually knows that there are two objects, and the second object happens to be inside the first one, right? So think about, how this could be used, for instance, thinking about occlusion. You're trying to spot a person, and suddenly he goes behind a wall. You no longer see this person, and such a model could potentially allow you to understand that this person is behind the wall, right? And he's going to be coming out at the next instant. We have applied it to a number of different applications. For instance, this is a case where there are two objects in front of you, the blue box and the yellow can, and I'm asking you to find the red can, okay? And in fact, you don't know where it is, right? You can't even see it. And what happens is that we allow the model to actually think about the possibility that behind everything, there is something that potentially is smaller than that, right? So it could be there are no objects, but there could be something smaller than it, right? So, so from this model, when you lift this blue box, right, so it could be that there's still no red can, or it could be that the red can actually turns up, right? So by having this kind of implicit constraint, the model can actually reason about things it's never seen before. We applied it to, things like the Mars rover, where you're trying to do what is called as planning. You're trying to understand how exactly, what kind of decisions are to be taken in a context where you don't know a lot of things, right? So if you think about one of these rovers on the surface of Mars, right, it has no idea what could be behind, stones, what kind of ground it would potentially find itself in. And you're able to do what is called as Markov decision processes, which is a framework from optimization to actually do planning. So the agent can sort of reason about what actions it needs to take to accomplish some objective. So one of the things we started to wonder is that, okay, all of these programs are very nice, but the key sort of limitation is that these programs are often given by us, us being people who work on these programming languages. And so the natural question is, well, can you learn these guys, from data? Okay, let's see what we're really trying to do. So this is a table right here, and it talks about, this records what is called as the happiness data set. So essentially, it's a survey from people across the globe, against various indicators like GDP, pension, age of retirement, and so on and so forth. And it's trying to measure, are these people happy? Right? So what you're trying to do when you try to learn these programs is that, you're looking at potentially the spread of values on any of these columns, right? So for instance, what does the happiness distribution look like? Are there countries where people are not happy at all, like completely unhappy? And are there countries where people are extremely happy, right? So you're trying to understand the spread of values is one thing. The second kind of thing you might be interested in is to try and understand correlations, right? So for instance, is there something to be said about GDP and happiness, right? And the answer is yes, of course, which is not surprising. Again, it's not a causal connection, right? It's not necessary that as soon as you have a high GDP, the country is going to be full of happy people, but there is a correlation, right? And in a more complex data set, in fact, this is what is called as an entity relationship model, and this is a fairly complex organization of some kind of company hierarchy, but it could be applied to other domains too. For instance, if you think about a student, he's got a student ID, he's got a date of birth, right? He enrolls in a number of courses, right? So this is a kind of structure I want to give to the machine learning model. Right? These models exist, right? So for a number of domains, from university data sets to companies and so on and so forth. So if this structure is available, can it be part of the machine learning pipeline? So when we do these unsupervised learning of these programs, can this be a kind of constraint that's telling the system, look, this has to be satisfied no matter what you do, right? So that's the idea. And what we were able to learn is these very interesting programs where, for instance, it shows that if a student who considers himself to be in the mid-level in terms of his intelligence, and he takes an easy course, but the number of hours in this course is quite high, it could be that his satisfaction is low. Right? Or otherwise, if it's an easy course with less number of hours, then the satisfaction is very high. Right? So you can understand the spread inherent in this data in a completely unsupervised fashion. And you can think about a university administrator is looking at this and potentially saying, okay, maybe I should be careful about putting out too many courses which take a large number of hours, and it should be reducing the number of hours so that the grade satisfaction as well as student satisfaction is a little more higher, at the same time achieving the objectives that I want in terms of my curriculum. Right? And one of the interesting things is that, when we actually look at a lot of these data sets, the kinds of data points that we see, don't satisfy the usual kind of extremes that we see, in typical machine learning literature. People typically talk of Gaussians and so on and so forth, and we see all sorts of funny combinations when we actually look at the data. So we do try to fit this model as closely as possible to the spread of values. This is another kind of program we learn where you can talk about what is the probability that the grade is high given some features from this data set, right? And the key point here is that it's all unsupervised, right? So we are not tinkering, we're not constructing these programs, and they're automatically learned from these programs. And hopefully this makes sort of a point towards interpretability and explainability. Sort of the counterpoint to that is, if this representation you learn is really tough to understand and read through, right, what are you going to do, right? So if you think about this program having thousands of lines, then it's sort of unrealistic to expect some kind of course administrator to actually go through these lines and try to make sense of what's happening, right? There is a way around it, right? One of the key ideas is what is called as abstraction. And abstraction says that if I'm a course administrator, then I don't really need to think about, the date of birth of students or the height of the students, so on and so on and so forth. So what I will be provided with is sort of a high-level interface, right, which only talks about the attributes that I care about. Right? So one of the interesting areas of research is really how do you construct these abstract representations that is sort of customized to some user potentially using this software. But if you really want to push it and you don't want to think about abstraction, you might say, okay, what if you really only care about queries, right? If you think about a database, we're not trying to, if you think about a database, query engine like SQL, you're not really trying to present some fragment of the database to the user. What you want to provide him is with an interface where he can ask queries, right? He can ask, how many people have a salary of greater than X pounds, right? So those are the kinds of things a database person wants to ask, and that's the kind of query interface that people will see. And in the machine learning setting, these won't be deterministic answers, right? So you're looking at distributions. So the kind of things you want to ask is if the height of somebody is greater than 180 centimeters and the weight is greater than 200 pounds, what's the probability that this person is male, right? So these are the kinds of queries you want to ask. And this is the only thing you care about right now, let's say, and no longer about the representation. So we started looking at a variant of deep learning models, which are also naturally generative. These are called as sum product networks. What's the key idea? Okay, if you look at this, this looks like a deep learning network, right? So there are a number of layers, there are inputs, but there's no output. It's just you just have variables at the very bottom and also the intermediate levels, right? And what's happening here is that this little structure here is actually a graphical model in disguise. So if you think back about the slide where I talked about these graphical models, this is somehow capturing a graphical model, okay? And the interesting thing is that it can be trained like a deep learning network, but on the other hand, you can ask it probabilistic queries like the ones I had on the previous slide, okay? So the question is, can we take these guys and potentially deal with, the kinds of complex data points that I talked about, like, the happiness data set where you have continuous spread of values and certain discrete entities and so on. And another way to think about how these sum product networks works is that if you try to understand what makes an office, right? And again, there are a number of features, right? For instance, it possibly has a window. I mean, if you're lucky. It may have a laptop. It may have plants if you're lucky, right? And again, a lamp itself is further thought of in terms of other compositional parts, right? For instance, it has a lamp stand, a lamp head, and so on. And notice that none of this is deterministic, right? It's not the case that an office has to have all of these components. It's just that there is some kind of probabilistic correlation between some of these components existing and forming an office room. So what a sum product network is really doing, and what all these x1s and x2s and x3s really tell you, is what these variables are. And they can appear at many points in this kind of deep architecture. Okay. And what we were able to show is that these kinds of architectures that can actually work very nicely with this happiness data set and other kinds of data sets. And the way they work is that it's a completely unsupervised regime. Okay, so if you think about, if any of you are familiar with some aspect of deep learning, part of the challenge there is trying to figure out how many layers do you need, what kind of feature engineering do you need, right? So the feature engineering doesn't necessarily go away because the X's and the X1s and the X2s are typically the features in your domain. But it's, once you fix these features, it's completely unsupervised, okay? So you let this data to this kind of learning regime, and it automatically constructs the right number of layers, and it provides you with this interface where you can ask things like, what is the probability that somebody is male given that they have certain features, right? And you can also swap them around. You can ask things like, if somebody is male, what does the distribution of the height look like, right? So that's the attractiveness. It's not really designed for one label. You can keep swapping them around, and you can imagine this will give you a different perspective of what is being said in your data. There are a couple of other nice properties about it. The key thing, as far as the computational aspect goes, so of course, there are many software packages right now which do deep learning, but nonetheless, these networks actually share many similar properties in being what is tractable, which means that you can actually ask these queries by simply doing a single pass over the entire network, which is not very expensive. It is very scalable as well. So I'm almost running out of time, which is good because I'm towards the last part of my talk. So now, as I mentioned, I wanted to spend a few minutes in the last part of the talk to talk about this idea of model responsibility. Okay, so as I said, it's a philosophically vexing theme, and there are many different aspects to really capturing the landscape of responsible AI. But the kind of thing that I have in mind is situations like this. So who knows what this is? A good number, okay, so this is what is called the trolley problem, okay? So it was principally studied by philosophers to understand what are the ethical principles by which we, which we guide ourselves by. And the setting is this, so there's a trolley that supposedly is going on its path, and without actually doing anything to it, it's going to be on that first track and potentially killing 5 people. Let's take the assumption that these 5 people cannot escape. Okay, so if the trolley is not disturbed, it's going to end up killing these 5 people. You are that person sitting, standing there who potentially has a kind of switch, and you have the ability to actually pull this switch, right? And what happens if you pull this switch is that the trolley gets onto the last track and kills 1 person, right? The reason this is so challenging is that it brings up the question, what is the value of a human life, right? And there is no way we can quantify something like that. What people, in philosophy have been trying to understand is what do, people really want to do in this situation. Some people would argue, I don't know the circumstances under which these 5 people happen to be on that track, so my job is to not do anything because maybe it's their own fault. And if I, take the option of pulling the switch, I have decided to actually take somebody's life, right? And the interesting thing is, if you ask the same people, what if it's the exact same story, but there are 5 children there, and they will almost always say they will pull the switch, right? So this just shows you how challenging it is to actually understand, this problem context. And the reason, this is a very extreme situation, right? So we have to be hopeful that in most cases where AI and machine learning is used, it won't be as extreme as this. But I think it still raises the question, what should this machine be doing if it has choices, and some of these choices potentially do impact people's lives, maybe as not as extreme as death, but something substantial anyway, okay? One of the key ways that computer scientists and mathematicians have started to think about this is what is called as causal models. And if you remember when I talked about, setting the stage, I talked about 2 kinds of, settings. The one case where you simply do what is called as conditioning, where you look at, the distribution when you set something to true. The second case is actually you try to intervene. You try to change and influence a variable, and you're trying to understand what's going to happen, okay? So what we have for doing or even thinking about those kinds of things is what is called as causal models. And typically they have the following structure. You have some number of exogenous variables. These are things you don't control, okay? You have some number of endogenous variables. These are things you can control and you will potentially control. And structural equations which brings these 2 things together. So this is just a simple setup here. So think about, back to the trolley problem, one of the endogenous action is pulling this switch, right? So let me say that you set this variable to 1 if you pull the switch and 0 otherwise, okay? Another endogenous variable is the outcome, right? So if I pull the switch, right, then there is this variable which says that 5 people die, right? And if I don't, let's consider another variable which is true if the person on the sidetrack dies, okay? And the way these 2 things come together are these equations like this, which says that T1 is 1 minus A. How that works out is that if A is 1, that is if I pull the switch, right, then the value of T1 becomes 1 minus 1, which is 0, which means 5 people haven't died, right? So this is just a way to actually talk about effects of actually setting, some variable. And of course, you could be uncertain about how any of this works. Okay, so that's where the probability comes in. So you have a probability distribution on the possible way the world works. Okay, there has been some very recent attempt to try and formalize what all of this means when you want to talk about the blame of a system. And roughly the idea is you think about what would happen if I do A versus A prime. And you understand the difference in terms of the cost. Okay, so, and again, cost is used as a proxy to understand the ramifications of some of the choices that you've made. So the kind of question we were interested in is, can you learn models of these kinds of model scenarios? The second question, which I'm going to sort of skip over, gloss over, is can these judgments be computed tractably? The main reason is that sometimes these decisions are taken on a split-second basis, and you want the approach to be scalable. And we sort of looked at this learning regime where what we're trying to do is we try to learn all aspects of the model here, okay? Everything from the distribution on these causal models to potentially some of these variables, as well as the costs that come into play when you try to understand the implications of your actions. Okay, so you're trying to learn aspects of these models, and what we also observed is that if you just let this unsupervised learning regime fly, it's going to struggle with the complex search space, and it actually helps to provide some interesting constraints to these models. For instance, one natural constraint is if I sacrifice myself by actually coming on to the track, at the risk, and again, the understanding here is that the trolley actually stops and doesn't go further, because then there wouldn't be a point in sacrificing yourself. If I sacrifice myself, then potentially somebody gets saved, right? So to learn these, we use these deep probabilistic models that I talked about in the previous slide, and we compute, the scores by iterating over action choices. And the key question is, can this system potentially align with the kinds of responses that people give, right? So we survey people to understand what they would do in a number of variations of the trolley problem and try to understand the kind of predictions we make, does it correspond to what people do. I only discuss here for the trolley problem because it's the most famous, but we also looked at a number of other settings like lung cancer staging. We are deciding, should I give a person radiation therapy or not? Right, a number of, the whole point of responsible decision making is, affects a lot of different domains. And so the setup we have is something like this. Okay, so the second track, so the main track has a number of these options. So for instance, it could be that the main track just has one person, the main track has 5 people, has 100 people. Right, and in all cases, it happens to be that on the other track, your best friend is there. So the question is, this is very extreme, I understand that, but the question is, are you willing to, what kind of choices will you make? And it's interesting to see, right? So on the left-hand side is what we collected from the survey, and the right-hand side is what we get from our system. And if you look at, for instance, the one which says family, you see that a majority of people do want to sacrifice themselves, right? Which makes a lot of sense because you care a lot about your family, and you're willing to pay the price of your own life for family, right? So again, a very extreme situation, but potentially the idea here is that in not so extreme cases, there might be a way to potentially inform the machine what kind of choices it should be making. This graph basically shows, the cost function which I talked about. As I said, the cost function is supposed to be a proxy for all the factors that influence your decision making. And we also see that the cost function we end up learning is quite close to how people think about, the value of certain choices, right? So what's interesting here is that if you ask a person for a number for any of these things, right, they wouldn't be able to give you, right? As I said, you cannot put a value in human life, but by gauging different situations and asking people for their responses, there might be some hope of understanding the implications of actions, okay? I'm going to wrap up in 2 slides. So the first one is that, as I mentioned, there are many opportunities. I tried to talk about 4 different perspectives on trying to attack these opportunities. I think that there's much to be said about how, and I hope you agree, how statistical approaches and machine learning approaches can potentially combine with symbolic approaches. As a very last slide, as I also hope to have told you that automated decision making brings up a lot of concerns, right? So it could range from ethical, like fairness, or moral, like blame. And it's really unclear the formal definitions that computer scientists are coming with align in any way with all the quantitative perspectives on the issue, right? But in fact, formal definitions is what we need to build systems. We hope, the hope here might be that there might be some way to essentially talk about this alignment between what a system learns and what humans are actually have in mind when they build some of these systems. And the takeaway message is that humans need to be in the loop, right? You can't build any of this. So even if you, automate one aspect of the learning, it's impossible that all dimensions of the problem really fit in without having a human in the loop. And that's it. Thank you very much.
Thanks, Vaishak. We're actually running over time, so we don't have very long for questions. I'm sorry about that. But any quick questions? I had a quick question, which is, so if I understood correctly, you're saying that your system, the answers that it gives, it corresponds to what, I think you said what people give.
Yeah.
But it's quite well known that people from different cultures give different answers to the trolley problem. So are you saying that your system...
No, I'm not saying it's a replacement for that. So
it's culturally specific.
Yeah, so the whole point here is that you're trying to learn these utilities, and of course they could be context specific. So you could make them context specific. So this is only indicative of the responses we have collected, right? So of course, if you collect responses from different cultures, it could potentially be that the utility functions we learn is going to be completely different. right? So we're not trying to provide a generic kind of recipe for all cultures. What we're trying to do is, given a subset of the responses, we're trying to learn a utility that matches what these responses say, as opposed to saying be normative.
Thank you. Any questions? One at the back. You have a microphone in your seat.
Very quickly, in the medical and general biological domain, whenever you want to do an experiment that involves animals, or more importantly humans, you have to go through a panel of bioethicists in order to have the experiment approved before you can do anything. Would you endorse such an approach also for, in general, the computing domain, now that we're going towards more and more automated systems?
If they have these kinds of ethical aspects, then yes. There are aspects of computer science that are very abstract, that don't really, touch on these issues, but there are also aspects, as you point out, which do touch on them. So having, and in fact, that's what most grant agencies do nowadays, that they do have a board which tries to ask you about what are the ethical implications of the research that you do. And the truth is that most pragmatic AI has some kind of ethical impact, right? Maybe you don't specifically look at an application, but somebody else could take your software and apply it to, for instance, surveillance, and then what do you do, right? So yeah, absolutely, people have to think about that.
For a fairly simple
You have a
model,
microphone right next to you. On your right.
Does it work? Yeah.
Yep.
Okay. For a fairly simple model like this, did you find that there are many local optima when you're fitting your model?
Yeah.
And in which case, what do you think that has some implications for more realistic models?
I think the part of the reason for this local optima is really the context, because again, if you get responses from different age groups, you'll potentially see a very different spread in how these responses come out. And I don't know what the good fix for that is. I think, in the end, if you think about deploying a self-driving car, right, it's sort of irrelevant what cultural context it comes in, because it has to make a decision. Either you don't deploy them, which is also a possibility, or you do deploy them and somehow it has to aggregate the preferences and the utilities across different contexts and different cultures. And that's not at all clear to me how it should be done. That's part of the challenge of this, right? So we can only hope that in some contextualized setting, we have some way of trying to understand implications, but at the broader scheme, it's quite an open question.
Okay, I'm going to ask the final question. Can you spoke about learning the program and learning the rules. Are you able to give us any technical details on how the data is represented, what the model looks like, how you learn the rules?
Yeah, so the data is relational, so it looks exactly like this little data set here, right? So you have a table typically. You can also capture these kinds of things as rules, so this could be a part of your background knowledge. And technical detail is as follows. What it tries to do is it looks at the spread of values. It tries to do this kind of decomposition and learn a function for those local spaces. And in the end, the empirical correlations are guided by this loss function here, which says that in a carefully defined hypothesis space, given this background knowledge, which could be a structure like this guy, how do I how do I minimize the loss, right? So it's trying to find a hypothesis space. It's trying to find a representation in this hypothesis space that most closely fits these examples, while respecting the background knowledge, right? So that's a key technical idea there.